Bridge Conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. The unloading is done in a predetermined order. All the hardware for the bridge, pins, bolts, and the tensioning rods are unloaded first. Next, the prefabricated bridge rails and the pier caps. Note the wooden blocks used to prevent the change from damaging the wood. The pier caps are set a measured distance apart. The pier caps will be used to provide support for the bridge deck panels. In effect, they are creating a field workbench. Throughout this installation process, you will see an almost complete absence of sophisticated equipment, unless you count the crane as sophisticated. The crane, a hydraulic jack used to tension the rods, are all that is needed except for the ordinary hand tools found in any municipal garage, pipe wrenches, sledges, crowbars, etc. This bridge will be built and placed with those tools and the township employees. That's one of the major benefits of modern timber bridges. Regardless of type, nailed deck, glue laminated, or pre-stressed, you need only the minimum of equipment and your own personnel. There are 4 prefabricated panels, A, B, C, and D, and here are the plans that show that. The plans may seem simplistic, and they are. Remember, one of the keys to modern timber bridge installation is that it can be accomplished by a semi-skilled workforce under the direction of your resident engineer or an experienced bridge construction supervisor. The 4 panels were pre-assembled at the plant and shipped with 8-foot thread bars, tensioned to keep the various pieces together. At the construction site, the panels are placed in pairs, panels A and B, C and D. The tension is released from the shipping thread bars, and the 8-foot bars are removed and replaced with bars 14 or 15 foot in length. Then they, in turn, are tensioned. The panels A and B are then combined to form one large panel, actually 1/2 of the bridge deck. The procedure is then repeated for panels C and D. You now have 2 half decks. The bridge pier caps are installed on the concrete abutments. The bridge site is now ready for the placement of the bridge deck. The first half deck is installed. When the joined panels, the half deck, are being lifted, the crane is lifting 20 tons and reaching out a considerable distance. So the crane must have a sufficient lifting capacity. The second part of the deck is positioned on the pier caps, an activity that combines machinery and muscle. The 2 decks are now seated but not joined. It is this joining process and the tensioning that makes this bridge type unique. The eye bolts used to secure the cable are removed. The decks are further aligned using this rod alignment tool.
Give me a little press time here.
The locking nuts from the interior side of the half deck are removed.
Go ahead. Go ahead.
The rods are turned out to a sufficient length for joining. This length is assured by the simple step of painting the ends of the rods with red paint. The rods are tensioned to a pressure equal to 90 to 100,000 pounds per square inch. The decks are pulled together by this tensioning. The rails and curbs are assembled and installed. A bituminous wearing course is applied and the bridge is completed.
I'd like to discuss the role that maintenance plays in assuring long life for timber bridges. First, a little background material. Wood is a marvelously adaptable structural building material. When it's treated with a compatible preservative to prevent early decay deterioration, it can certainly be an economical, practical, and long-lasting structural material, and it's particularly adaptable to short-span bridges. Structural wood has many advantages. First, it's simple to fabricate. It's lightweight and easy to install. It has a high strength-to-weight ratio. It does have excellent sound and thermal insulation properties. Has good shock resistance. For example, the AASHTO bridge specifications don't require impact loading for timber members used in bridges. It has good fire resistance. Large structural members, when they are subjected to flame, they develop a char layer that effectively insulates the wood and slows the burning rate, so that a high percentage of structural strength is maintained for considerable periods of time under fire conditions. Wood is totally immune to commonly used de-icing chemicals. It has unique aesthetic properties and qualities. It is a renewable resource. It's one of our few building materials that you can farm and get crop after crop. It is economical, and it's long-lasting when it's properly treated and protected. Some of these properties, its inertness to de-icing chemicals, and as well as some new design developments such as glued laminated deck panels and pre-stressed laminated decks, make it more desirable than ever to use in highway structures. Another area that can add to the lifespan of timber structures is attention to design details in the design phase of timber bridge construction. Some of the things to pay attention to, that designers need to pay attention to, are to use only wood species that are readily and effectively pressure treated. For exterior use, oil-borne pressure treatments are more effective than water-borne treatments. All wood should be completely fabricated before it's pressure treated. Avoid design details that trap water and dirt and other debris. Avoid the use of boxed heart wood members to minimize the development of checks and splits in the wood. When it's practical, use glued laminated members. Avoid using roll roofing or sheet metal caps on stringers, pile, or post tops. And as much as possible, make bridge decks an impervious roof over the stringers. I think one of the most important factors in assuring long life for timber bridges is an effective inspection and maintenance program. If we have thorough periodically scheduled inspections by qualified inspectors. This is the key to an effective maintenance program, and we can significantly prolong the useful life of timber highway bridges. Timber bridge maintenance can be divided into three categories. The first is preventive maintenance. In this area, decay is not yet started, but conditions which are conducive to decay are present. Moisture control and some in-place preservative treatments are probably the most effective maintenance measures for preventive maintenance. The next category is early remedial maintenance. In this situation, decay is present in the wood, but if corrective measures such as in-place treatment and perhaps replacement of some of the minor members such as curbs and railing members are done, the structure will be able to remain in service for many years to come. And then the third category is major maintenance, major rehabilitation or replacement. Unfortunately, most timber bridge maintenance is ignored until it reaches this stage. In many cases, replacement of most of the timber members is necessary if it goes to this stage. Okay, in summary, wood is good if timber bridges are properly designed, constructed, and most important, properly maintained.
Okay, as discussed, my topic today is wearing surfaces of timber bridges. We use many wearing surfaces for timber bridges. The purpose of the wearing surface is to save the timber from structural wear. The different materials that we use are aggregate, native soil, timber running planks, full width running planks, steel running plates, actual laminated decking, asphalt, such as asphalt pavements or chip seals, and other innovative types. All of the above wearing surface treatments are effective depending on the traffic types and the maintenance that is used to treat the bridge. This paper discusses existing timber bridge wearing surfaces throughout the nation and Alaska, and discusses trends and coming attractions. The typical timber bridge is flexible and, like other bridges, typically has joints. It is the joints that cause problems in cracking, pulled nails, loosened bolts, interlaminate wear, and surface wear on any bridge wearing surface, whether the native material for the bridge is timber, concrete, or steel. I'd like to discuss each type of wearing surface separately, including preferred applications and their strengths and weaknesses. As you'll see in the paper, there are schematics and photos of in-place bridges illustrating the use of different materials and the relationship between the deck and the wearing surface. I'd like to start with the aggregate or native soil surfaces, in that it's the one that's been used historically most. Native soil and aggregate are very easy to apply and very inexpensive, except the problem comes with moisture and the collection of moisture on the bridge deck and the wearing of the timber bridge because of the aggregate that abrades the wearing surface. The moisture also is a problem with timber deck, and even though it's inexpensive, there are some maintenance problems, and probably you lose some life of that bridge. The timber decking for running planks is very inexpensive also, but the life of it is somewhat limited. You might get 5 to 10 years of life on running planks. If you only use the running planks that are maybe 3 or 4 planks wide, you end up with possible maintenance problems in between the running planks and some wear in the decking at that level. That's why in our region, one in the Forest Service and in other places, you'll put the running planks, the timber running planks, the full width of the bridge, and therefore you avoid the wear in between the planks because you've got a full width. There is some moisture problems with this type of running planks because it does collect between the planks and the actual deck. Also, you have some problems that the nails that you use to tie the planks to the deck cause holes that moisture can get into and wear the surface from moisture getting in, and also bacteria and fungi that do eat on the timber. If you've got a treated timber deck, if you put the running planks on, you break through that treated layer and possibly moisture and fungi can get on into the center of the wood that is not treated. The next type are these steel running plates, which have many of the problems that the timber has. Some of them last long, but many times the steel running plates will get torn up by snow plows or other type of maintenance equipment. We typically don't use the steel running plates anymore in that they do become a maintenance problem, even though structurally they're very sound. After the steel running plates, many times the actual laminated deck is used and no running surface is put on it or wearing surface is put on at all, in that if the traffic is low, structurally it's sound, and if there's not too much traffic, you don't have a problem. It's the excessive traffic and maybe aggregate and different other abrading items that get on a wearing surface that will wear the deck. But if the traffic is low, you can get by without the running planks or plates. Usually when you get into larger traffic volumes, you'll end up trying to use the asphalt wearing surface. We have a problem with many timber decks. The joints are the problem, so you do need a very solid timber deck to avoid cracking and propagation of cracks from joints through the asphalt wearing surface. If we talk about the types of bridges that we're putting in now from decks, the old nail laminated decks used to have quite a bit of delamination, and so you had a joint between each lamination, and many of those would cause alligator cracking in the asphalt, and the wearing surface would break up, and you might not get more than 5 years of life from it. The glue laminated decks, where you had 4-foot wide panels, reduced that cracking, and the only places we normally would see cracks then are between the joints of the planks. We have gone further with that and have used dowels, which sometimes helps reduce that propagation of the crack between the glue laminates. Beyond that, in the recent past, in the last 5-10 years, we've used some geotextiles between the decking and the asphalt wearing surface, which reduces the propagation of those cracks. We've had some bridges in over 5 years with no measurable cracking because of the propagation. A couple of the brand names are Petrotech and Repave. Both seem to be effective. With the new stress timber decks that are coming out now, there are no joints in the deck, and maybe even a chip seal will afford a wearing surface that's adequate, especially on lower trafficked roads. On these asphalt wearing surfaces where we go beyond the chip seal or the double penetration treatment, we use 1.5 to 3 inch wearing surface that'll give you a 10-year life at least, similar to an asphalt road surface. Some we've gone as much as 20 years. The Ontario government in Canada has had some 10-year life bridges that are stress decks that are still working effectively with the asphalt wearing surfaces. That pretty much covers the types of wearing surface that we have on the timber bridges. In summary, we have many varied wearing surfaces that do work, and the economics depend on the traffic that's utilizing that bridge. I think that for many existing bridges, you can go through and put new wearing surfaces on them effectively, whether it be planks, plates, or asphalt wearing surface. In the new proposed designs, the asphalt wearing surface is very effective and can be used, and you do not have to fear the cracking between laminates.
Build better and safe with modern timber bridges. This was the theme of a nationwide timber bridge conference held in May 1987 at University Park, Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. State and local assistance programs, from the Pennsylvania viewpoint, was the subject of a talk by Arthur A. Heim from the Ben Franklin Partnership.
The purpose of my program is to discuss state and local assistance programs and projects as they relate to the Timber Bridge Initiative. Through the course of the presentation, I'll be talking about several of the state-funded activities, their mission, and some of their initiatives. The first program I'd like to relate to is the RTAP program. RTAP is an acronym for the Rural Technical Assistance Program. RTAP is co-sponsored by the Pennsylvania Department of Transportation, the Federal Highway Administration, and the Pennsylvania State University. RTAP's mission is in technology transfer, in bridges and roadway and highway construction. RTAP provides this technology transfer through workshops and one-on-one consulting activities. The contact for RTAP is Ms. Ellie Snow, S-N-O-W, at the Pennsylvania State University, University Park, PA. The second program I'd like to discuss is the PENTAP program. Again, an acronym for the Pennsylvania Technical Assistance Program here in Pennsylvania. It's a program jointly sponsored by the Pennsylvania Department of Commerce and Penn State University. Like the RTAP program, PENTAP provides technical assistance to Pennsylvania business and industry, local municipalities, and communities. The purpose of the PENTAP program is is to provide assistance and state-of-the-art technology, techniques that may be helpful to business and industry as they carry out their mission. Its purpose also is to take research that exists within educational institutions and essentially get it out to the field where it can do some good. Both the PennTap program and the RTAP program are free to the user. They're without charge. The contact for the PennTap program is Dr. Leroy Marlowe. He is located at the Pennsylvania State University at University Park, PA. The PennTap program can also be accessed through any of the Penn State Commonwealth Education campuses spread geographically across the state through the continuing education departments at those campuses. The next program I'd like to describe is through the Department of Community Affairs in Pennsylvania and the Bureau of Local Government Services within the Department of Community Affairs. This Bureau's mission is to provide one-on-one consulting activities to municipalities, again in areas of highway or road or bridge construction, any area of interest that would relate to local municipal needs. The primary focus of this department within DCA is in areas of training and technology transfer. In the technology transfer, we're looking at taking some of the resources that exist within Pennsylvania and relating them to local municipal needs. And in the training area, this Bureau designs and develops programs, again, that relate to local municipal needs. The next program I'd like to describe is through the Pennsylvania Department of Transportation and its Bureau of Municipal Services. This program is operated through 34 statewide, or 34 offices spread geographically across the state. Each one of these offices relates to a specific municipality. Again, the mission here within the Bureau is to provide assistance to municipalities, that assistance relating to highway, bridge, and road construction activities. Also, this department is responsible for allocating the liquid fuel dollars and helping municipalities access those fuel dollars. The contact is Jerry Kirkpatrick. He's the director of the program at the state level, and again through the local municipalities, local offices at those municipalities. The next program I'd like to describe is the Ben Franklin Partnership Program. Again, a program co-sponsored by the Department of Commerce, funded by the Department of Commerce in Pennsylvania, and managed through the 4 advanced technology centers in Pennsylvania. The mission of the Ben Franklin program is to work in applied or targeted research, education and training programs and activities, and enterprise development activities. It works through jointly sponsored partnership programs that share the cost of transferring technology, applying research from a research base to a technical need that exists within a community. The program is currently funded at roughly $26 million and matched with a little over $100 million in private sector funds, supporting well over 500 separate projects in Pennsylvania. Again, the purpose of the Ben Franklin Partnership Program is to look at an identifiable need in a community that relates to some level or some form of technology and match that with a resource that exists somewhere within the research base and provide matching funds to support the development of a research or training initiative. That program can be accessed through any of the advanced technology centers, any of the 4. There's one here at Penn State University, and I myself am the contact point for that program.
The topic I would like to talk about is bridge funding. I would like to explain how your municipality can qualify for available state and federal aid and what funds are available. First, concerning your bridge funding eligibility. The first requirement is that your bridge must be put on the Pennsylvania Department of Transportation's bridge inventory. This is accomplished by having your bridge inspected and a report sent to the Pennsylvania Department of Transportation office. Second is that the bridge must receive capital budget approval. This can be accomplished through the legislative process or by contacting the appropriate Pennsylvania Department of Transportation district engineer. Third, the State Transportation Commission must approve the project. When commission approval is given, your project is placed on the Commonwealth's 12-year transportation program. So again, to become eligible for bridge funding, it is necessary to have your bridge placed on the bridge inventory, receive capital budget authorization, and be approved by the State Transportation Commission. Next, concerning what funds are available. The Pennsylvania legislature authorized bridge funds for state-owned and locally owned bridges when it passed the billion-dollar Bridge Bill 1 in 1982, and again with the passage of billion-dollar Bridge Bill 2 in 1986. This legislation provides for more than $3 billion to be used for bridge repairs and replacement for over 4,300 bridges in Pennsylvania. Of the 4,300 bridges identified for rehabilitation or reconstruction, approximately 50% are on the local system. We have a listing here that shows how locally owned bridges qualify for funds. This chart represents a breakdown of federal, state, and local participation. If your bridge does not qualify for federal money and it is on the billion-dollar bridge program, the state would pay 80% of the monies necessary, and your municipality would be required to pay the remaining 20% share. However, if you are found to be eligible for federal critical bridge funds, you can receive 80% of the money needed to get your bridge reconstructed or rehabilitated. The state would provide 15%, leaving your municipality with the remaining 5% share for the total project. We also have a funding source for urban, primary, and secondary funds, which can provide 75% federal money and 20% state money, again leaving your municipality with a 5% share. Keep in mind, you can use liquid fuels money for funding your local share of this project. Additionally, the Department of Community Affairs provides municipalities with community development grants which can also be used for your share. In closing, in order to determine if your municipality can become eligible for these funds, you should contact your respective Pennsylvania Department of Transportation district engineer in your area. Thank you.
Pennsylvania. The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges. Howard Jerusalem, the Secretary for the Pennsylvania Department of Transportation, provided the welcome and overview of the needs and markets for modern timber bridges. Here is a brief part of Secretary Jerusalem's address.
On December 8, 1982, our first billion-dollar bridge program was passed. In 2 months, we went from a dream to probably the biggest bridge building program in the nation, and maybe in the whole world. Approximately 1,000 bridges for $1.4 billion. I'm happy to say that we're moving ahead on those bridges. We've had about 650 of those bridges are either open to traffic, having been completed, or they're under construction for about $850 million. About 70% of the time has passed, and about 70% of the bridges have been built. And they were the major bridges, and they might not have suited themselves to timber construction. But then last year, we had a second billion-dollar bridge program passed, and that included 3,300 bridges for $1.6 billion. And of those 3,300 bridges, 1,650 were local bridges, low-volume rural bridges, the type that will suit themselves to possible timber construction. So I think having this conference today is certainly appropriate when you realize the type program that we have. I did look over the agenda, and I noticed that it includes all facets of timber bridges, including materials, design, construction, and maintenance. And there were 1,500 covered bridges in Pennsylvania, and now we only have 250 covered bridges. And they were victims of flood, fire, and lack of maintenance. Also, we didn't have the proper preservative treatments for timber in those days. Well, those technical difficulties can be overcome today. So I think it's very timely. Governor Casey has also made it clear that his #1 priority is economic development. And perhaps if we can start building timber bridges in Pennsylvania, it will be a boost to the economy of the Commonwealth. We have the materials here, and we have the expertise here, and it can mean jobs for Pennsylvania. And I don't expect that the major bridges will be built using timber, but those 1,650 local bridges that I spoke about, many of them will suit themselves to timber construction. And maybe we can come up with some standard bridges that can be timber for some of the very short span bridges that are included in the billion-dollar bridge program too. The money's there. The time is to move ahead, and let's start getting the job done. Timber bridges offer aesthetics that no steel bridge can match. Some people say this is beautiful or that's beautiful, and of course beauty's in the eye of the beholder. But a timber bridge that's molded into a rural environment is something that I find beautiful. And I hope that, this conference can get us on the way in Pennsylvania to doing that type of project. Well, there are some obstacles to getting timber bridges to be a reality. I know they're building one today or placing a timber bridge today, and I'm looking forward to the completion of that project. I hope you all have a very good conference, and I hope that it results in the people from Pennsylvania anyway coming back and thinking about timber bridges as an alternative, because I think it can be an economic boom to the Commonwealth, and I think they are the most aesthetically pleasing bridges that can be built. Thank you very much.
The economic impact to local industry and to the Commonwealth of Pennsylvania was addressed by the Honorable John Peterson, Senator from Pennsylvania's 25th District.
As Howard talked, for Pennsylvania in particular, and I think for eastern United States in general, Pennsylvania being a state with 66% forested, and much of Pennsylvania working to rebuild their economy, the timing of this conference just couldn't be any better than it is. I want to congratulate everyone that had anything to do with putting this together, because what you're doing is you're raising the knowledge level, you're raising the issue of bridges being built out of timber, and when you have your start-off speaker, and I was very pleased with Howard's embracing comments that timber bridges can be and will be a vital part of our $2 billion bridge program. But I would like to say you started out with two politicians. Howard may not consider himself a politician, but anybody that's head of a department in Harrisburg is a politician, or he wouldn't get those jobs. And he's lasted through 2 administrations, so he's a good politician. He's done a lot of things right. But you started out with the politicians, and I wanted to compliment you also on your agenda, the kind of people you have here today. I felt, when I read the agenda, I said to my staff member, Vince, I said, gee, what I'm doing speaking at this group, the experts are all here, and all the people with the information that's needed are here. And maybe what I say will be more general, because I certainly wouldn't want to get specific with the kind of experts that you have here. But I would say, you know, oftentimes politicians get accused of speaking out of different sides of their mouth or saying things in different ways when they're with different groups. But I heard a story that I think sometimes explains how the pressures of the day, not only for politicians but for people in general, somewhat color what they have to say and how they say it. It reminds me of the story of the Pennsylvania Dutch farmer who was walking down the road one day taking his cow Bossy to market. And as he was walking along, suddenly around the bend came a truck at a high rate of speed and sideswiped him and the cow and knocked him into the ditch. Well, about 2 months later, this farmer was in court trying to get damages from the trucking company who had been unwilling to pay. And he found himself in the witness stand trying to get what he deserved, but find it very frustrating with a high-priced big city lawyer really making it difficult to get his story across on how this thing really happened. And the lawyer said to him, sir, he said, did the truck driver not walk back to you and ask you if you were hurt, and you said no, and I want a yes or no answer? Well, the farmer sort of hesitated. And he said, well, it wasn't quite like that, sir. He says, I was walking my cow Bossy down the berm of the road, and he said, swish around the bend, come a truck at a high rate of speed, and the lawyer jumped up and he says, I object. I asked for a yes or no answer, and I didn't get it. I want a yes or no answer. Well, the judge said to the clerk, would the clerk please reread the question and ask for a yes or no answer? So the clerk repeated the question. Did you not tell the truck driver when he come back to you and ask you if you were injured, did you not say no? Well, the farmer hesitated a little longer, and he said, well, it wasn't quite like that, sir. He says, I was walking down the berm of the road with my cow Bossy, and then the lawyer jumped up and said, I object, and the judge said, sustained. He said, let me ask the question. So the judge repeated the question, and he said, now, could you please give a yes or no answer? The farmer hesitated, and he says, well, judge, he says, I was trying to explain. And the defense attorney, he says, I was walking down the road with my cow Bossy, and the defense attorney started to get up again, and he said, the judge said, sit down. He said, I'm going to let him go on. Maybe he'll get to it after a while. So the farmer went on to try to explain. He says, I was walking down the road, down the berm with my cow Bossy, and he says, swish, around the bend came a truck at a high rate of speed, and he said, knocked us into the ditch. He said, the truck went on down the road till there was a wide berm, and he pulled off. And he says, the truck driver got out, and he walked back to the cow first. He looked at the ditch, and he saw the cow was beyond repair. So he pulled out a gun, and he shot her. He says, he walked back to me with his gun in his hand, smoke coming out of the barrel, and he said, are you hurt? I think that explains the situation sometimes from which we have to speak and the pressures. And it's not true just to politicians. I think it's true to life. Sometimes at home, maybe. It is a pleasure to be here today. And I feel that what you're doing is exactly what needs done. And I really, again, want to compliment you. I think this symposium is one of the real bright spots that's happening not only in Pennsylvania but in this part of the country that is raising the awareness level of one of our great resources. We wonder why more bridges. As you look at the national statistics I saw where 11% of the bridges are wood, and I think in Pennsylvania it's a very low percentage. And you wonder why. Well, having been in the process a number of years, when you look at the lobby of steel over the years, and Pennsylvania being one of the major steel producers, they have lobbied hard for steel bridges, for all sizes. And this morning I was having breakfast with a friend who just happened to be here, but he's in the construction business and the aggregate business, and when he heard we were speaking at a timber bridge conference, he says, timber bridge conference, he said, what's wrong with concrete bridges? Well, there's nothing wrong with concrete bridges, but there are places where timber bridges ought to be considered. But the concrete and the aggregate lobby have been strong voices, have been strong lobbies over the years, and have been successful. And that's the political process. That's the way government works. They respond to those who educate and raise the awareness level. And what you're doing here is going to raise the awareness level that timber bridges have a part in our solution of rebuilding and replacing our bridges, not only in the Commonwealth of Pennsylvania, but in this country. And so I just can't commend you enough for what you're doing and what you're doing to bring this issue forward. Pennsylvania, I think one of the, Howard mentioned, the governor's #1 priority is economic development. It's been my #1 priority as a state senator, not because I wanted it to be, but because it's the necessity of my district. I represent a large rural district, 8 counties, almost an eighth of Pennsylvania in geography. And the economy in my region has declined because of steel and glass and manufacturing declining simultaneously. And our major problem, the major issue I work with daily, the major issue that I need resolution to, is rebuilding and stabilizing our economy. Last night, just to show you what we've been doing, we had a meeting here with a number of Penn State officials, a number of people in the hardwood industry across Pennsylvania, again, working towards developing a program for Pennsylvania. So we have some priorities in Pennsylvania so that we start looking at our timber as a resource and as one of the major ways of rebuilding our economy. We've sort of ignored this resource in Pennsylvania because we have been a steel state, we have been a manufacturing state, and we've had other parts of our economy that have kept us healthy over the years, that have been growing and strong, and we've just sort of paid very little attention to the utilization. Pennsylvania, in the last 2 decades, has not had a plan of how to make timber, our timber resources, a part of our economic base. We don't even have good data in Pennsylvania of what kind of species we have, what will be available to market year after year or 10 years down the road. We don't even have records and statistics of what we're doing with the finest quality hardwoods in the world, the cherry and the white and the red oak. We don't have statistics on how it's being utilized, where it's going. We know a lot of it's being exported, a lot of it in raw form, log form, and rough cut form. We've been working to develop a plan in Pennsylvania so that we, #1, inventory this resource, have some projections of what potential it has in the future, and how it can be, the secondary processing can be a major part of revitalizing much of rural Pennsylvania, who has this resource that's been taken for granted. So your program today ties right in with what we're doing, and certainly using our Pennsylvania forests as a resource to rebuild our bridges. I represent 142 municipalities. Now, a lot of senators, I was talking with someone last night, and I think one of the cities of Scranton has 3 House members and 1 senator. Well, I represent 142 communities, 8 counties, and 29 school districts. So I get into the problems of a lot of rural communities. And as the $2 billion bridge program is approaching, many of those bridges, as Howard said, are rural, local bridges. And I don't think there's a month goes by that we're not working with a local government who is struggling to find money to replace a local bridge. And unfortunately, we've not had a plan in Pennsylvania as one of the alternatives of replacing them with wood. I think there are many communities in the last 10 years that I've served in the legislature and the 8 years that I served in local government before that, there are many instances where local governments would like to have had an option. When you get in rural Pennsylvania, you don't have the expertise, you don't have the proliferation of bright consultants, and you don't have the know-how there, and you become much more dependent on leadership from state government. And I'm delighted that Howard's receptance to your program and to wood being a part of the future, and I'm going to be working with the department, and I see you have municipal services people speaking later in your program, so that the Department of Transportation, because they have a lot to say with how local governments spend their liquid fuels money, which is the money they use to fix their road and bridges. And many things have to be pre-approved and can be pre-approved. So I think, like I said, the timeliness of this symposium is just couldn't be better. Couldn't hit us at a better time, because in the next 4 or 5 years we're going to be rebuilding most of our rural bridges. Now, if my memory is correct, the second $2 billion bridge program has more bridges in it than we can afford to build with the revenues that will generate in that period of time. Now, it's my view that if we get our act together as far as wood is concerned and get this alternative out there, a lot of our rural bridges, and I'm sure you're going to have people here with statistics, I'm not going to get into that field, but from the information I have as a generalist, the information I've read, a lot of our rural bridges can be replaced with less expensively than with concrete and steel, and thus our bridge program can go further. We can reach further out to the smaller, more rural bridges and really resolve Pennsylvania's problem. Pennsylvania, a decade ago, when I first got in the legislature, was facing a horrible problem of bridge decay. I mean, we had a time bomb ready to go off, and I want to commend Tom Larson and Howard Jerusalem, who's been certainly one of his stalwart underlings through the years, for getting us and for leading the legislature into a major bridge building program, and now into the second one, and probably we're going to need a third one. But we're out ahead of many states in rebuilding our bridges. We've done most of the major crossings. If you came from the east, you probably came across the Clark's Ferry Bridge. I think that was a $7 or $8 million structure, a beautiful bridge across the Juniata. And we're making great progress, and we're down now to where we're going to be getting out into the country, and we're going to get into the bridges that your symposium can have an effect on. So I guess in conclusion, it seems to me that if we continue with the efforts you've started, and I certainly will be selling this concept in the legislative process. As Howard mentioned, the aesthetics of wood bridges, maybe the legislature ought to be setting a priority that in our state parks and our areas that are high in tourism, on certain on roads with certain traffic counts, that we ought to be, our first priority ought to be to put in a wood bridge. I think they're much in Pennsylvania, especially western Pennsylvania, where I'm coming from, and northern Pennsylvania. Tourism is going to be one of our future economic tools for economic growth. And to me, in our state parks and our areas where we have a lot of tourists, wood bridges should be maybe number one priority in replacement of our small rural bridges. So I guess in conclusion, I want to commend you for what you've done and those who have organized this conference and put together, because what you're going to do in Pennsylvania and surrounding states, you're going to raise the awareness level that wood should be a part of the solution of rebuilding our bridges throughout this Commonwealth and in each and every one of our communities. And I congratulate you and promise to you that I'll lead the fight in the legislative process to help make this a reality.
As Senator Peterson commented, rural areas and timber bridges go together. But it hasn't always been easy to get them together. A cost comparison of timber bridges was provided by N. Stewart Gilson, Secretary of Milford Township, Juniata County, Pennsylvania.
Then in 1980, we got a federal bridge survey. That shook up one of the supervisors. I had a concerned supervisor from that point on. In 1981, we got a new supervisor, then I had a concerned majority. They gave me the permission to research timber bridges. Our first experiment was to be a conventional type bridge, 22 foot long, with girders and horizontal plank set on edge, and it came through beautifully. I had a friend design it for me. Then I took it to our engineers, or rather the engineers in Harrisburg, and they approved it. Then I gave it to our Sanders, Walls and Rye, who designed it and adapted it to the condition, and it came out fine. So as of this date, we have 3 completed bridges now with a total savings of over $200,000 under the estimates from the federal inspection. We have 2 of those bridges that have unlimited weight, no posting. We have 1 bridge with a 28-ton limit. That's this one.
Milford Township currently has 3 timber bridges in place. Bridge construction since 1982 had a total estimated cost of $401,000. An actual cost of $83,067. The resulting savings, $317,933. You can build better and save with modern timber bridges.
Treated timber has been used in Ohio for several years. In fact, many of our early bridges utilized treated timber as their main components. We used, back in the 30s and 40s, a lot of steel beam bridges with setting on timber abutments, timber piers, with also timber decks on top of steel beams. We refer to those as the strip floors. The one problem that, basically the only problem that we had was the leakage down through the boards. Salt water and whatever would leak down between the boards and corrode the steel beams underneath. So we started looking for some alternative methods, and we became familiar with the glue lam deck system, which is basically a strip floor, but instead of the boards being individually nailed together, the boards are glued laminated, thus making a watertight floor system. So we, back in '76, built our first structures, or rehabbed our first structures using the glue lam deck system on top of existing steel beams. That system worked pretty well. We learned several things as we built the 2 projects, but one was a steel beam bridge and one was a truss bridge. It was rehabilitated. In both cases, the glue lam was specified with no alternatives, and then after it was installed, then asphalt was laid over top of the glue lam for the wearing surface. This system worked quite well, although the glue lamming itself is quite expensive. We felt that it was worth the extra cost to basically waterproof the floor and to protect the steel beams underneath. Then we became familiar about 3 years later, in '79, we became aware of another system of utilizing treated timber, and that was what we refer to as the longitudinal deck system, which did not utilize glue laminations, but basically the individual boards were dowel laminated or friction laminated together into manageable widths, pre-fab panels, if you will, in 4 to 6 foot widths. And those were then utilized on some structures. The advantage of that system is the fact that you can eliminate the structural steel underneath the bridge altogether. The deck itself spans from one abutment to the other abutment of the bridge, and you really don't need to glue laminate. At least our theory is that they do not have to be glue laminated, because leakage through that system will not affect the steel, since there is no steel underneath. So we became aware of the system based on a couple of the county engineers' experiences in Ohio, and we took a look at their systems and liked what we saw. So we proceeded to specify an all-timber bridge utilizing the longitudinal deck system. That happened to be in a state park area and fit in real nicely with the surrounding area. And that was built in 1979 and came out a real nice structure, nice looking structure, and very functional. Completely timber, all timber, no structural steel in the bridge. Since then, we've utilized the longitudinal deck system for some small short span replacements where the abutments can perhaps be reutilized, but you eliminate again the structural steel and the strip floor. Many of these have been installed with our own crews because they are easy to handle and they're quick to install, and they just work out very nicely. Then also one of the other timber products that we've used quite a few of is the timber box culvert. We found that again, it's a prefabricated system that works very well for use with your own crews, and also in low pH areas, in mine acid areas especially. These systems, or that system, has held up very well for 20, 30 years with minimal or zero maintenance, basically. So we've also experimented with the timber box culverts and have utilized several of those in the southern part of the state. So all in all, we're pretty happy with the longevity that we get with treated timber. If it's properly designed and properly installed, it should last 40 or 50 years with minimal maintenance.
Mr. Gilson's comment about the impact of the federal bridge inspection is but one aspect of the concern that the federal government has about timber bridges. Here is John J. Alscott, Chief of the Bridge Management Branch of the Federal Highway Administration, speaking on the challenge of timber bridges.
In my capacity as Chief of the Federal Highway Administration's Bridge Management Branch, I'm concerned about timber bridges. I'm concerned that they are disappearing. Right now, timber bridges constitute about 10% of the nation's bridge population. There are 576,000 bridges carrying public roads in the United States, and roughly 60,000 of them are timber bridges. That's very significant, but it becomes less significant when you consider that just 5 years ago, in 1982, there were 70,000 timber bridges carrying public roads in the United States. What has happened in the last 5 years? Well, each year, the federal government, through the Federal Aid Highway Program, helps fund a $3.6 billion bridge replacement, rehabilitation, and improvement program. How many bridges a year does that account for? Last year, it was 6,500 bridges were approved under that program. 99% of them were concrete or steel. Only 1% of those bridges were timber, masonry, aluminum, or other structures. That's significant. State and local governments also carry out bridge programs with their own funds, such that we estimate that about $5 billion with a B are spent on bridge improvements each year. But timber right now constitutes a very small percentage of the funds. I think that part of the problem that people are facing in the United States is a perception problem with timber. For whatever reasons, most of the public, many engineers, legislatures, and what have you, conceive that or perceive that timber bridges are not economical, do not last long, and are not safe to use. This may indeed be wrong. We think we need to do some things with regard to that to make sure that timber, which can provide a very competitive bridge in many situations, receives its rightful share of the market and at the same time enters the competition for the public dollar that all of us involved with public works should be striving for. Another area where timber bridges can play a bigger role is that of alternate designs. We at the federal government encourage competition between different materials, different construction techniques where it can be used. Timber certainly can play a bigger role than it plays right now. We know that we've had some great competition between steel and concrete at particular bridge locations where they've both been suited, and we think that timber, particularly for local governments on local roads, may play a much larger role in competing one-on-one against alternate materials. Moving on, there's another perception that the public has with regard to timber bridges that is somewhat borne out by the facts. Nationally, about 41% of our nation's bridges are classified as deficient. By deficient, I don't mean unsafe. I mean that they don't meet today's standards. Roughly 240,000 of the nation's 576,000 bridges are classified as either structurally deficient or functionally obsolete. By structurally deficient, they have inadequate load capacity. By functionally obsolete, they may have a geometry problem, too narrow, maybe inadequate vertical clearance. Nationally, the average is about 40 to 41%. The existing timber bridges that we have, the old ones in place, the 60,000 timber bridges or so that we're using every day, the percentage is 83% of those bridges are classified as deficient. Now that's a problem, a perception problem that people have to face up to. The new technology in timber treatment, the technology in design can result in some bridges which will move timber into its more rightful share of the market. Not every place, and maybe not on the interstate highway system, but the fact that about half the nation's bridge needs are on local roads and streets, and the other half are in the most important areas, such as the federal aid highway system, tells us that there may be indeed a very large marketplace for timber as a competitive material on local roads and streets. And I'm looking forward to conferences such as this one I've just participated in promoting such an endeavor and improvement in the competition and use of timber bridges.
An overall introduction to timber bridges was provided by Clyde Weller, the Chief Structural Engineer of the United States Department of Agriculture, Forest Service Division. Here is a portion of Mr. Weller's presentation.
The purpose of this workshop is timber bridges. I've been asked to do an introduction about timber bridges. I'd like you to know that I'm feeling very positive about timber bridges. Timber is a very viable material for both substructures and superstructures for local, rural, state, and even interstate bridges. Not only highways, but railroads and trail bridges can be made using timber. In the Forest Service alone, we have timber bridges in all corners of the United States, from Alaska to Florida, from New Hampshire to California on to Hawaii, and all points in between. Timber has many advantages that will be discussed in the next 2 days at this workshop. Quickly, the advantages of timber are it's easy to fabricate, it has a high strength to weight ratio, it has good sound and thermal insulation capabilities, it has excellent shock resistance. In fact, ash tow requires no reduction for impact loadings for timber, whereas it does for steel and concrete. It has good fire resistance. It's immune to de-icing chemicals. It is a renewable resource. It has good aesthetic qualities. It also has long life, as long as it's pressure treated to avoid some of the disadvantages of timber. To be fair, there are a couple of disadvantages to timber, and I need to address those for you so you know how to treat the disadvantages. The two disadvantages are that timber does decay and it does have a moisture problem. Structurally, when timber is too wet, the strength is reduced, and when it decays, the strength is also reduced, in that you have all seen rotted timber. And due to those two weaknesses of timber, we must pressure treat it for long life. A quick summary on what it should be treated with, in my mind, we need to treat with an oil-borne rather than a water-borne treatment. Creosote and pentachlorophenol are the two typical ones that we do use. After it's been treated with these materials, we find that it is protected from moisture and the fungi that does eat on it. Let's talk very quickly about some of the types of bridges that will be discussed during this workshop. We'll probably touch very briefly on native stringer bridges in that historically many of these bridges were constructed. There was no treatment, therefore the life was not long. Since the life was not long, many people found that they were looking away from timber as a material for bridges. Since we've learned how to treat timber, we find that it has long life, and we have many new ways of treating timber, and a few of these new methods I'll talk about. One of the methods after we started treating timber was that of nail laminating timber decks. The nail laminations typically delaminated with much traffic, and again, timber had a bad name. With those delaminations and the history had with that, our Forest Products Laboratory did research and learned how to glue laminate timber. This material has been used over the past 20 years very effectively. We find that bridges that have been in for 20 years look as good as new. Some of the new materials that we have come out with now are stress timber. Ontario, Canada, has come up with a stress timber bridge that wipes out the remaining disadvantages of timber. Glue laminated timbers typically had joints between the sections, and those joints, as in any bridge, such as steel and concrete, are the problems with bridges. With stressed timber, no joints are necessary. The other important aspects of stressed timber are you can use shelf-size lumber to construct the bridges with. Both cross-section and length are reduced. We now can build long sections of timber with just butt-jointed laminations, and we create a bridge that serves as an orthotropic slab. Beyond the decks of bridges, from a substructure standpoint, we have both timber cribs, timber abutments, and piles that are used in the substructures. Very effectively, we use this material in all of the different road, railroad, and timber bridge or trail bridge areas. This very critical area of timber bridges, or any bridge, is the water and air gap, where the water rises and falls and the material is exposed to air and exposed to water intermittently. Treated timber piles work very effectively in this area. So as a quick summary, I'd like to express how positive we are now about timber, the new methods of longitudinally laminated, glue laminated bridges, and stressed timber bridges. You'll hear of all these things in the coming 2 days of this workshop. Thank you.
The conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges.
The use of prefabricated timber bridges is widely accepted, and the most prevalent type of prefabricated timber bridges is the longitudinally dowel laminated timber bridge. Research was undertaken to extend the range of span lengths over which that type of construction could be used. And we looked at a method that was developed in Ontario for pre-stressing of timber transverse to the member. And we looked to use this method, this technique developed to develop longer spans for our timber bridges. In order for you to have a better understanding of why we were looking at the pre-stressed timber, it's helpful to understand what we're currently doing. The most cost-effective timber bridge built today is a dowel laminated longitudinal bridge deck. But this bridge has several drawbacks. All of the members with that type of bridge must be continuous. They're made up of 4-inch plank that are placed on edge, and then they are laminated together with dowels, 3 16-inch ring shank dowels that are 15 inches long. The depths of the planks vary with the span, and they vary from 8 inches to 16 inches for spans from 12 to 42 feet. This bridge is prefabricated in a plant and then shipped to the job site in panels which are about 6 feet wide or 6.5 feet wide so they can be shipped. Then they're assembled at the bridge site on the caps using a shiplap type joint. This bridge can also be equipped with a 10-kip rail and it'll meet all of the federal funding on it. When we looked for a method of extending the range of that type of bridge, we looked at some technology, as I said, developed in Canada for that. And as any new technology is tried, two questions really have to be asked. One is it applicable to the problem at hand? Most of the bridges in the United States are somewhere between 20 and 200 feet in length, and so we really were looking for technology which would apply to that range of span lengths. And the second question is it better? And in the case of bridges, really you were talking, is it more cost effective? Now, our preliminary investigations indicated that the type of technology developed in Canada would be applicable for bridges 20 to 200 feet in length. And as we started to look at the cost and some of the other ramifications of it, they appeared to be cost effective in the longer spans. So we embarked on a program to look at that. And as I started to review the design specifications that were used in Canada, it became very, very obvious that one must look at the social economic environment in which bridges are built, because specifications tend to reflect the pressures in the marketplace. We as a company know of many construction techniques that are technically feasible but economically impractical. And so the real question that we wanted answered was not whether pre-stressing worked, but rather, would it work in our market area? That was the question. Most of the bridges built in Canada that have been built using this system were built by equipment and crews of the Ministry of Communications and Transportations. They have equipped a truck with all of the necessary jacks and pumps to simultaneously stress all of the tendons in an average-sized bridge simultaneously. In our market area, most of the bridges are built by contractors under contract, and we felt that it wasn't reasonable to assume that a contractor would have to invest in lots of equipment merely to install a timber bridge. So the first question we wanted answered was, can it be done with one jack, one pre-stressing jack? So we designed a bridge, a test bridge, to be tested at the University of Wisconsin, and that was one of the questions which Dr. Oliva was to look at, is could we put uniform pre-stress in all of the rods using only one jack. The bridge that was tested was 48 feet in length, is about 9.5 feet wide, is made up of 16-inch deep timber, 4 inches wide. The longest plank in that bridge was 20 feet, even though the span was 48 feet in length. We used 8s, 12s, 16s, and 20-foot plank. The results of that testing were encouraging. So then we looked for a site where we could actually build a bridge, and we found a site in northern Minnesota and a client that was willing to buy the bridge, and we built a 44-foot pre-stressed timber bridge. And at this point, the question now was, can we prefabricate large components and assemble them in the field? That was really the question. And then the other question was, is it going to be cost effective? So we designed a bridge. Again, we used the Ontario Highway Bridge Design Code to determine the resisting moment, and then applied an HS-20 load to it. And that was the basis for our design. We built the bridge. The bridge was installed by the maintenance crew of Cook County in 2 days. The cost of the material delivered to the site was $25,000, and that included the abutment material. The county estimates that their costs, absorbed costs, were about $10,000, which is their men, equipment, and some crane rental. The total cost of the bridge per square foot was a little over $34 per square foot, which is very competitive for a bridge. The neat thing about it is that we went up to northern Minnesota in the middle of February, and we blasted out the abutments about 10 o'clock one day, and by noon the following day the traffic could drive over the bridge. It was incredible. Our experience in constructing the bridge in Cook County and also the bridge in the state of Pennsylvania have substantiated our earlier conclusions that the technology of pre-stressed timber is applicable, it is practical, and it is cost-effective. The major benefits to be derived from the system, first of all, is that we can use non-continuous members. Now, the cost savings in buying shorter members is offset by the cost of the stressing system. But the two other benefits from an engineering standpoint to be gained from using a pre-stressed longitudinally laminated deck is, first, the distribution width of the wheel line is much greater. Our data from the tests at the University of Wisconsin indicates that the actual distribution width of a wheel load is about 67% greater than the assumed width in the AASHTO specifications. This makes timber a more efficient material for highway bridges. The second advantage of a pre-stress system is the fact that you create a very efficient load-sharing system between the individual laminates. You create a system in which now the weak member no longer determines the strength of the system. They act in unison, and they either all fail together or they stand together. And consequently, we can use much higher design values for exactly the same material if we are putting them in a pre-stressed situation. Therefore, the technology of pre-stressing material for timber bridges is going to go forward. It's applicable, it's practical, and it's economical.
Okay, basically what I'm talking about is the use of glue laminated timber for vehicular and pedestrian bridge use. And basically I'd like to define the term glue laminated timber. And glue laminated timber is actually the process and the manufacturing process of bonding for bridge use dimensional lumber, 2x4s, 2x6s, and so forth, with an phenol resorcinol glue. And basically what this does, you create a member basically to any width and to any depth and length up to approximately 75 feet that is stronger than most solid pieces that you could find, if you could find that size. The advantages of going glue lam over, say, these solid sawn materials are, number one, on the larger sizes of the solid sawn material, there could occur a high moisture content before the preservative treatment and the fabrication of the bridges. If this moisture content is in the wood, what could happen when the bridge is in use is that the wood could dry, causing severe cracking and checking and allowing the presence of fungus and organisms to decay the wood. But with the glue laminated timber, basically during the manufacturing process, all the lumber is kiln dried. When it is glued, all the fabrication can be done in the plant, and then it is sent to the preservative treater for the treating. And what you end up with is a completely prefabricated product, and with the proper treatment, which in our estimation is the oil treatments, it preserves the wood to a point where no excess moisture will occur inside the beam to eliminate any future checking or cracking. There is, in laminated timber, a high degree of quality inspection and testing that has to be done during the manufacturing process. Just briefly, some of the items that are done are a proof loading machine that tests the finger joints of the individual boards so that the boards can be made to any length required. Example, if there was a 75-foot long bridge, the individual boards before laminating will be made to a length of 75 feet by the process of using finger joints. And again, the finger joints go through a testing machine. They are broken to failure to determine that the bonding strength of the glue is adequate and that the finger joint strength is reached. They have also cyclic delaminating tests and shear block tests. A cyclic delaminating test is actually taking samples of the wood, placing them in an autoclave with pressure added with water, and basically creating an accelerated exterior exposed condition by producing this pressure upon the piece. And after that's taken out of the autoclave, they can determine that the glue is proper, the material is proper, and it could withstand the pressures of being used in the exterior use. Shear block tests are basically what they say. The individual pieces or the blocks used are put under a shear loading to determine the shear strength at failure. And in most cases, that shear strength at failure is much greater than what was designed for. They have a moisture scanner that the lumber goes through, and basically the moisture scanner is sensors that the lumber passes through to determine the moisture content of the wood before it goes into the laminating process. If the moisture content exceeds what they are looking for, what the allowable is, generally 19% and less, the lumber is then sprayed and removed from the process and taken back to an area to be re-dried before used again. And the only other machine that really does some more testing and on a technical standpoint is an RF console, which is a radio frequency controlled console that will accelerate the bonding of the glue of the finger joints. After the finger jointed material is bonded, it goes through a tunnel, and a radio generator actually starts creating a standing wave in that tunnel that'll excite the molecules of the glue, which will enhance and accelerate, again, the bonding of the finger joints. And that is another reason why it is good to have kiln-dried wood, and it's necessary to have kiln-dried wood, because if the wood had any certain moisture content going into this RF console tunnel, the molecules of the wood would be excited and the wood could heat up. So it is a good idea in that aspect to use the kiln-dried wood. Basically, through the laminating process, again, the kiln-dried wood is finger joint to length. The individual boards are cut to length. It goes through a gluing process where the wide faces of the boards are glued. They're placed in a rack, and the rack subsequently is tightened down to a certain pressure so that if you were making a 48-inch wide panel, 40 feet long, the panel would be made at a 48-inch dimension and tightened down with hydraulic jacks. And basically the jacks are spaced 18 inches to 2 feet on center. After that process is done, the material has to stay in the jacks for a period of 24 hours under strict environmental conditions. The glue has to be in a certain temperature, in the room temperature, for it to adhere and dry properly. And after the glue has dried, the material is taken out of the racks and has gone through a planing process to determine the actual size of the panel. They could make the panel thinner if they have to. They could make the panel less wide if they have to. And also, there's been a lot of concern about paving and adhering to the timber surfaces. The surface of the bridge can be specified to be rough, and that the underside of the panel may be plain smooth so that it would set on the abutments or the steel or whatever on it nice and square. All fabrication is done in the plant. It is true that there are a lot of instances in the field, and AITC allows this for field fabrication, holes drilling, end cuts, what have you. Of course, they do recommend that the preservatives be applied on those field cuts, but generally most of the fabrication will occur in the plant. And that is just done by the craftsmen, people with tape measures, drill bits, drills, and different machinery to fabricate off a set of shop drawings. After all that work is done, the material is then ready to go to the preservative treater, and depending on what the project is specified for, it would go to, again, one of the main 3 treatments, either the 2 oil treatments, creosote or pentachlorophenol in oil, or if it has to be the CCA, which is a water treatment, it'll be done before the laminating process. And we do strongly recommend that in using glue laminated timber, the oil treatment, the treatments do be used. Basically, we feel that the oil gives a better coating, a better surfacing to the wood through extended period of use than the water treatments do. Another item about the water treatments is that in the processing of glue laminated timber and the water treatments, before the material is manufactured, the individual boards are treated. Once they're treated, they're brought into the plant. They have to be surfaced. After they're surfaced, which is basically taking off some material and treatment off the individual boards, they are then laminated in the process I mentioned earlier. And after that process is completed, they are planed once more, again planing off more of the treatment. So we do feel that the oil treatment does offer a better treatment, a better condition for the wood to give a long-lasting life.
Conference dealt with the design, construction, installation, and maintenance of modern timber bridges. Leading up to the highlight of the conference, the actual erection of a modern timber bridge. National and local experts discussed the need for modern timber bridges and cost comparisons between timber bridges and more conventional types. They also related their practical experience with modern timber bridges.
My comments today are made from the perspective of being the chairman of the AASHTO Timber Bridge Committee and as a state bridge engineer from the state of Minnesota, where we construct annually approximately 25 new timber bridges per year on county and local road systems. This accounts for approximately 1/3 of our new bridge construction on local roads and county roads. We have found through the years in Minnesota that timber bridges do have several advantages. One of them is the ease with which they can be constructed, and also the minimum amount of inspection that is required at the bridge site. From the national perspective, bridges generally are designed using the AASHTO bridge specifications, and these specifications are developed by representatives from the 50 states across the country, and the Subcommittee on Bridges and Structures is composed of the 50 bridge engineers from across the nation. Currently, in our Timber Bridge Committee, a subcommittee of AASHTO, we are reviewing the shear specifications for the floors and also for the stringers, and especially in the stringer area as it relates to bridges that are in place, timber bridges in place. We're looking to modify these shear specifications because they do tend to govern some of the designs and some of the ratings for the in-place bridges. Another new development that's coming is the requirement by the Federal Highway Administration that railings on bridges be crash tested. Now, many states, and Minnesota being one of them, have crash tested guardrails for many years. But now we're having a new requirement come to crash test bridge rails. And in AASHTO, we currently have a committee that's working on draft specifications for performance levels for bridge railings. And we're working on 4 different performance levels that would depend on the average daily traffic, it would depend on the percent of trucks, and the geometric conditions at the bridge sites. Now, the 4 different performance levels would be crash tested for automobiles and pickup trucks for the lower 2 levels, and for intercity buses up to 40,000 pounds for a higher bridge railing, and also for a semi-tractor trailer truck for the highest level of railing. For timber bridges, we would anticipate that we would use the lower 2 performance levels, and these rails would have strengths that would be equal to the 10-kip current AASHTO railing or somewhat less. The conventional rails that you see on most timber structures would need modification because we feel that as you would crash test them, you would probably have a problem with vaulting, where the car would actually tend to vault over the railing. And so we feel that conventional timber rails will need to be modified. As far as future trends for railings, we see the need for crash testing. And future trends in general for timber bridges, we see 2 of them coming. One is crash-tested rails, and the second one is the need to have specifications for stressed wood design. In Minnesota, we have developed a new timber rail, a jersey shape that's similar to the concrete railing in shape, and we've developed this out of glulam material, and we feel that this kind of a rail would meet crash testing requirements. We've also placed 1 experimental bridge in the stressed wood category, 1 pre-stressed or post-tension bridge similar to what's been constructed here in Pennsylvania as part of this timber conference. And so we see those 2 areas as new trends: crash testing of bridge rails and also new specifications for stressed wood design. I would just like to assure you that AASHTO in general and the Timber Bridge Committee in particular will continue to work with industry as joint partners in the development of new and innovative bridge design.
As a district bridge engineer for the Pennsylvania Department of Transportation, I've been involved with timber bridges since the early 70s. The first bridge was constructed by a municipality in 1974, and my office had the responsibility of approving plans for that bridge. Since then, a number of additional bridges have been built on local roads, plus 1 on the state system. I've reviewed the inspection reports on those bridges to determine how they are faring through the years. 4 of the bridges, it was noted that they're in need of major deck maintenance. 2 of them have substructures that are in need of minor rehabilitation. On 3 of the bridges, this is of a total of 10, the waterway adequacy of the bridge was deemed to be marginally adequate. And on 4 of the bridges, the roadway approach alignment was again deemed to be marginally adequate. In this investigation, I have several observations. One is that the bituminous wearing surface that is placed on the timber deck has invariably cracked on these bridges. Some of them have cracks in the bituminous wearing surface that are ½ an inch wide. This is largely because of differential movement that does occur between the deck panels on the bridge. And as noted earlier, poor stream alignment is a reoccurring problem on these bridges. We also have some a little more serious problems with the substructures on 2 of the bridges. The timber bents that support the superstructure have moved and now are slightly out of vertical alignment. Also, the timber lagging that retains the approach embankment on one of the bridges, this timber lagging is cracking and failing. I want to indicate that there are not serious problems, but they do point out design problems, things that were not considered in enough depth during the design process of the bridge. Next, I'd like to indicate to you some what I feel are advantages of timber bridges, and they certainly do have advantages. They are pre-engineered, and they are fast and very simple to erect. It can often be done in a period of several days. They're cost competitive. Notice I did not say they are necessarily the most economical solution. They are a cost-competitive solution to your bridge replacement problems. They're lightweight. This has relevance when we're dealing with existing substructures that perhaps can only support a lightweight superstructure. And another advantage in a rural area, especially the timber bridge does blend well into the environment. There are also a number of disadvantages. Some of them I've alluded to earlier, but we'll go discuss them again. A timber bridge is more flexible than many other bridge types. What this means is that when a load crosses the bridge, there is often a perceptible deflection in the bridge. This was of concern in our district. A bridge was used heavily by trucks. Some people living near the bridge very definitely noticed the bridge flexed as the heavy trucks crossed. It took some discussions to convince them that this was not a structural problem. This was inherent in timber bridges. Being light, they will tend to float if subjected to peak flows that would overtop them. So tie downs to ensure that the superstructure does not float away oftentimes have to be incorporated into the design. The pressure-treated timber surface of the deck is quite slippery, especially when wet, and this mandates the need for some type of a wearing surface. General wearing surface that's used is a bituminous wearing surface. The superstructure is generally deep. This is important when we have a crossing where the distance from the roadway grade to the stream bed is minimal. The deep superstructure can present problems in catching debris and so forth during periods of peak flows. There is also a tendency for timber to creep under dead load. This means that the bridge might initially be straight. In time, it could develop a bit of a sag such that water could accumulate on the deck. And as with any other bridge, periodic maintenance is required. There's a need to tighten the fasteners, and periodically, because of the cracking problem with the bituminous wearing surface, it will have to be replaced to restore a satisfactory riding surface. And the treatment barrier itself, that must be inspected to ensure that the coating or the protective pressure treatment is intact. Without this treatment, of course, rotting and other decay of the timber will occur. It's been my experience that the economy of a timber bridge is in large part due to the use of an economical substructure. In most cases, this means a timber bent substructure. If a concrete abutment type substructure had to be used, the cost advantage of timber bridges would be diminished significantly. Because of this, there have been some cases where the timber bends have been used when perhaps another type of substructure, although it would have been more costly, would have provided a better long-term engineering solution. The timber bridge can be damaged quite easily. One method of damage is by wear of tires. This is another reason for using a bituminous wearing surface. But perhaps more importantly is damage to the underside of the bridge, in particular the pile bents, due to collision with debris that flows down the stream during periods of peak flow. I have some recommendations regarding the use of timber bridges. You have to recognize that a timber bridge is not an ideal solution for every bridge engineering problem. It does have its places to be used. It does have places where it is not appropriate. And there are places where timber bridges, along with other types of bridges, are both appropriate and both cost competitive. In those cases, I strongly urge that the agency that is contracting for the bridge specify equivalent alternates. That is, allow the marketplace to determine the specific type of bridge that will be built at the site. This does necessitate having good specifications so that you are indeed specifying equal alternates. Use good engineering in the design. Frequently, especially at the municipal level, engineering is viewed as an extra cost. In other words, wasted money. I hope I've been able to indicate that this is really not the case, that by using good engineering, you can minimize problems that will occur throughout the life of the bridge and probably result in a bridge that's going to serve for a longer period of time. Some factors in engineering: adequate waterway opening, use an adequate bridge width, design for heavy enough live loads. In Pennsylvania, for our state system, we use the HS-25 design loading and 125% of the alternate military loading. I would encourage the municipalities and all those designing timber bridges to utilize this loading. I can't stress too much the importance of proper stream and roadway alignment, design of bank and stream bed protection, trying to minimize the potential for stream scour during periods of peak flow. And again, good, complete specifications so that the contractors know what you want and can provide an accurate bid. Contractors should be pre-qualified to ensure that you're getting the bridge that you've specified. In the inspection of that bridge after it's constructed, it should be inspected once every 2 years. Preventative maintenance then can ensure that the bridge will continue to perform for an extensive period of time without any need for major repairs. In summary then, a timber bridge can provide a viable, cost-competitive solution to your bridge replacement problems. It can only do so if you ensure that the bridge is properly engineered and properly constructed and properly maintained throughout its life.